Hey guys, welcome to Auto 56. Tonight we're going to be talking about engine blocks and what we call a short block. I'm going to pull up a PowerPoint and we'll get through this. We'll probably get through the first half today, and I'll finish recording the session for the rest of the PowerPoint either later tonight or tomorrow. So anyhow, next week we will definitely be in the lab. Tonight, we're just going to be going through this PowerPoint, and you guys can continue your work on chapter 20 and 21. Some of you have started chapter 22. That's awesome. Let's keep it up. I'm going to go ahead and share my screen now. Remember, if you have any questions, please email me, and I'll be sure to address those questions as soon as possible. And I just want to make sure that I'm answering all of your questions, because that's why you took this class. So let's see if I can find my screen here. We're going to share this screen, and you guys should be seeing my presentation here. All right. So there's that. So this is engine blocks. All right, well, hopefully you guys can see that okay. This is all engine blocks. We're going to talk about short blocks here. So the engine without the, did I jump ahead already? Here we go. The engine without cylinder heads, the assembled part of the engine without cylinder heads, is referred to as the short block, also known as the block. So the part that is actually considered the block is this part here. So on this page, there's some major components that you will need to remember. You not only do you have the block, in the block, you're going to have some core plugs, water jackets, you have the deck, cylinder bores, piston pin, also known as a wrist pin. So you also have the connecting rods and bearings, the crankshaft, and the girdle or main journal caps. So this is the breakdown here of what is contained in the short block or engine block. This is an example of a horizontally opposed engine. So on this horizontally opposed engine, what they're showing you here is just the configuration that the engine block has to be in. So the cylinder head sits on the sides of the block, and the block usually has cylinders that are separate from the block, from the crankcase itself. So this was included in the chapter, and I wanted to make sure that I touched on the orientation of the pistons and the direction that they move. This here is called a foam engine mold or core. I have this window for Zoom that is always in the wrong spot. Forgive me, guys, for the screen jumping around. This is your foam engine core. So what this is the piece of material that is used for casting the engine. So in the casting process, they actually pour molten aluminum or molten iron into a casting. This foam fills the area of the casting where the molten aluminum or molten iron will take shape. So as you pour the molten iron, this foam kind of burns away, and then as the molten iron solidifies, this is the shape that it takes. This is a kind of an example. So if you visualize the blue foam, the blue part in here as the foam, the molten metal displaces and vaporizes the foam pattern, and then the tan area with black speckles, that's sand. So as we pour our molten metal into the mold, the foam burns away and the sand kind of holds everything in place, and then we get what you call an engine block casting or cylinder head casting. Many parts of the car are built this way. So this is called pouring a mold or the casting process. One of the things that needs to be done when we pour a casting is we need to plug some of the holes. Because of the casting process, we have to leave some openings in the engine block so that the molten metal can run out. There's room for the foam core to hold its shape. And one of the ways we do that is by leaving these openings. Well, to close these openings, we use something called a freeze plug or pour plug. When we discussed cooling systems, we talked about the function of the freeze plug or core plug. So besides plugging the hole, one of its other functions is that if the water in the engine block freezes, the theory is it should push the core plug out before it cracks the engine block. Does it always work that way? Not necessarily, but it is a mechanism that's designed to protect the engine block. After you cast the engine block, you're going to have rough surfaces all over. So the first step is to begin the machining process, where you cut away all of the excess material that's not needed. And then you do a final machining process where we actually cut the cylinders perfectly round. We machine the deck so that it's perfectly flat. We thread all of the holes that need to be threaded. We machine the journal for the crankshaft. We machine the journal for the camshaft if it's a cam and block engine. So that's part of the process of building the engine block. This is an aluminum engine block. One of the things you'll notice that's different from aluminum engine blocks to cast iron blocks is that aluminum engine blocks actually have a lot of this webbing. So you'll see a lot of this webbing and ribs. This webbing and ribs, they're designed to actually strengthen the block because aluminum is a softer material, so it does require a little bit of strengthening. One of the other things about the aluminum block is the cylinders that you see here are actually iron cylinders that are pressed into the block. So these cylinders here are pressed into the block, and they've been machined with a cross-hatch finish. You could see the cross-hatch finish is like scratches at 45-degree angles. Those are very important because what those scratches do is they hold oil into the cylinder wall so that when you are when your piston is reciprocating up and down in the cylinder, it always has a film of oil on the cylinder wall. The next part here, we're going to talk about the crankcase a little bit. So in the crankcase, there's a few components and a few things that we want to look at. On this page on the top right, there's more ribs and webs. You guys can see that up close. On the left side there, we're talking about the crankcase. Inside of the crankcase, what we're looking at here is we have an oil pickup tube and an oil pump. This particular engine, the bottom end of the engine is the crankcase, but in the crankcase is this oil pump. This looks like an Audi or Volkswagen product. You can tell by the stamping. And then this gear is driven by a chain, which is connected to the crankshaft, and that is what rotates the oil pump shaft. And that's how we pump oil through the engine. This particular engine here, this is the crankshaft snout. And that crankshaft snout has a machined section so that it rotates rotors inside of the oil pump. This crankshaft it serves two purposes. It's the main crankshaft of the engine, but it also drives the oil pump. So this is what we call a direct drive oil pump, excuse me. All right, so what we're looking at here is these are the main journals, and the main journals are the part of the engine block that hold the crankshaft in place. So there are a few designs here that we're going to talk about. So you have the typical style journal, which is this guy here on the top left. In the old days, they used to say, hey, it's got a 4-bolt main or 2-bolt main. So this being the main journal is where the crankshaft, it's the bore where the crankshaft rotates. So that bore is actually machined with those caps bolted in place, which means those caps are not interchangeable. So if I remove a cap, I have to put it on in the same location and the same orientation as when I removed it. This is one of the challenges with the traditional or typical style crankshaft journal, okay? Once we kind of moved away from this, we got into engines and started making more power. They were a little more precision. We got into this cross bolt style journal where we have 2 large bolts, but then on the side of the journal, we have these small bolts that go into the side of the engine block. So that kind of helps strengthen the block, hold everything together, and take the additional forces from the high-powered engines of today. And then a lot of manufacturers are now going to this girdle design that you see on the bottom left, where all of the journals are integrated into a giant girdle, which is actually the bottom half of the engine block. So that's one of the things that, that has been going on. One of the things I wanted to say, though, it's very, very important that when we rebuild engines, we mark these journals or these caps, and we put them back in exactly the same location and orientation. So you got to visualize a perfect circle that's been machined, and if I change the caps, the circle's not going to line up. So you're going to have 2 half circles that are not properly aligned if you put the journals in the wrong location. All right, next slide here. This is the cylinder walls. So the picture on the top left here is called a, excuse me, this is a cast iron block. These are cross hatches. This bore is machined directly into the block, and you can see the finish there, that cross hatch I was talking about earlier. It's super important to have that cross hatch, and even when you're doing a piston ring replacement, it's really important to use like a ball hone and just do a cross hatch on the old smooth cylinder walls. And what that does is it restores the ability for the cylinder wall to hold oil. This picture on the top right is actually, it's kind of hard to tell. This is a water jacket on the top, and then we have the thin aluminum cylinder wall, and then the dark line here, this is actually a cast iron sleeve that's pressed into the aluminum engine block. So again, you see the crosshatch section there. Even though you can see that crosshatch, it's very smooth. You can drag, you see here somebody drug their fingernails across it. You cannot really feel those scratches, but you can definitely see them. So this is an aluminum engine block with a cast iron insert. This is a cast iron block with the machined crosshatch finish. And then down here on the bottom left, I have an image of cylinders, cylinder inserts. So the one on the far left is just an insert that gets pressed in. The one on the far, in the middle has like a lip on it. And then the one on the far right is actually the type of cylinder sleeve that is designed to get replaced. So like on some heavy duty diesel engines, you can actually replace the cylinders in the block. This is handy for, let's say, the engine is inside of a giant boat or a ship. The engines usually in a ship are so large that you can't really remove them from the ship. So you have to replace the components. And you might have to replace a cylinder that's 4 feet long and 2.5 feet around. And this is how they do it, is with these giant replaceable sleeves. The next thing I want to point out here is as engines rotate and function, let's look at this image here on the left. This is a image of a piston moving down. The crankshaft is rotating clockwise. And what's happening is there's combustion forces here pushing the piston down, right? So that piston is actually pushing the connecting rod, which is pushing the crankshaft. So if we look here, what's happening is because the force is going from the center of this crankshaft journal through the connecting rod into the piston, it's actually driving additional pressure on this side of the piston. This is called your major thrust. So as we have an explosion on top of the piston and it forces that piston down, you get a major thrust on this side. So what that means is for many engines, you will have more wear on the piston and the cylinder wall on this side of the engine. And that could be the left, right, front, or back of the engine, depending on the orientation and style of engine in the vehicle. On the opposite side, you have a minor thrust side because all we're doing is compressing air. There's not any explosion or other forces happening on the upstroke. So as that crankshaft continues to rotate clockwise, we're pushing the piston upwards, and that the direction of the connecting rod identifies the location of the force. So what we have here is we have force on the opposite wall, but that's called a minor thrust. So because we have a major thrust and minor thrust, pistons are designed to have an offset pin. This is something that may not be noticeable to the naked eye, but in this image here, and this image has been exploded for this presentation, but on the left side, from the outside diameter of the piston to the center of the wrist pin is 43 millimeters, and the outside diameter from the right side to the center of the wrist pin is 38 millimeters. So that 5 millimeter difference actually allows that piston to be more balanced and wear more evenly because of the major and minor thrust that I explained on the last slide. When we are looking at pistons, on the top left here, we have a piston, and that's piston is kind of machined out for the valves, so that the valves don't interfere with the combustion process. On the right-hand side, on the right top, we have a piston, the wrist pin, circlips, and the connecting rod. So these are all the components for the piston connecting rod assembly. On many designs, one of the things we have to do is we have to install this connecting rod into a heater, like on the bottom right image. And what that does is it heats up the connecting rod so that the small end, and that's the technical term for it, the small end of the connecting rod will expand. It'll expand enough so that the wrist pin or the piston pin can just drop straight into that connecting rod. And then as it cools off, it actually squeezes that wrist pin so that it holds it in place. So there's a couple of different styles where you can have a floating wrist pin, which is this style, where you should be able to push it in and out by hand. But then we have a pressed fit one that requires a heater. Oh, I jumped slides. It requires a heater to install that wrist pin. And then this is an image of a wrist pin connecting rod on the bottom left, wrist pin connecting rod and piston all assembled, and that's what it looks like. So I actually have personal experience with this. I was going to try to replace my pistons on a Jeep that I rebuilt the engine on, and I made the decision to send it to the machine shop because I didn't have the heater to heat the connecting rods like in this image. It cost me $12 per piston. There are 6 pistons. I think I ended up paying them like $78 to do that for me. That was one of the biggest expenses I had in rebuilding the engine. So when you know how to do most of this stuff, rebuilding engines can be relatively inexpensive. I actually had a YouTube video up of me rebuilding my Jeep engine, and I can't find it, so I don't know what happened to it. But if I am able to, I'll repost that. It's kind of a long video, but I rebuilt the entire engine in my garage, and I just want you guys to know it was less than $500, and I was able to do it myself. I have some special tools, but not many, so it's all possible, okay? This is kind of a cutaway of a piston, if you will. And what the image is showing is that we have a heat dam slot. So what that means is on the top of the piston is where all the action happens. This is where the combustion happens. So the top of the piston gets really hot. So up here, the piston's pretty thick. It's able to withstand a lot of heat. But as that heat conducts through the piston in the rings, it would transfer into the skirts where it makes contact with the cylinder walls. So to prevent the skirts and cylinder walls from getting too hot, they actually have spots on the piston where it's just a slot, and that slot is designed to slow down the heat transfer between the top of the piston and bottom of the piston. It's called a heat dam slot. You'll notice also this piston has grooves. These are called piston ring grooves. So we'll be talking about piston rings in the next session, and then hopefully for part 2 of this presentation, we can go more into piston rings and talk a little more about pistons and their function in the engine. So we have compression ring 1, compression ring 2, and this is called your oil ring or scraper ring, okay? Oh, I think I jumped ahead again. Here we go. So there's a couple types of pistons. So on this top left image, there's a picture of a flat top piston, and then there's a picture of a dome top piston. And the reason I share that is because the flat top piston, even though the stroke of the crankshaft is the same and all of the other features are the same, the flat top piston gives us an 8-to-1 compression ratio. Well, if I was building a performance engine and I wanted more compression, I can use that same engine and replace the pistons with dome top pistons, and that's going to give me a higher compression ratio. So that's one of the things that you can do for performance engines. Or you can go the other way. If you had a performance engine with a 10.5-to-1 compression ratio and you wanted to turbocharge it, one of the things you would do would be to convert it to flat top pistons. So this is what the different pistons look like. This one here is a domed piston. So it doesn't look like a dome, but this section right here is actually raised, so it actually protrudes into the combustion chamber. On the bottom left here, this is a concave piston. Where we see most concave pistons is on diesel engines or small engines. And the reason for the concave is sometimes the concave is used as the combustion chamber itself. For example, a diesel engine, the cylinder head on top is perfectly flat. There's not very much of a combustion chamber, if any at all. So they use a concave piston to take the place of the combustion chamber. This piston here is a flat top piston. So you can see the piston's mostly flat on top. Okay, and then this one here is a concave piston also, or they call this recessed. It's recessed, concaved, okay? So the difference is the concave piston actually has a big opening. The recessed piston is just a short opening. Okay. Now I was trying to find a piston that had a really strong identifying mark. This one has it, but it's not easy to see. But this piston has a little mark right here on the edge, and that identifies what we call the front of the piston. The front of the piston is identified by a little mark, and that little mark is supposed to point to the front of the engine. The front of the engine would be the side of the engine. For most cars, the side of the engine where the belts and the fan are located. So by pointing that to the front of the engine, that's going to give us the offset part of the piston to be on the correct side of the engine. This way we can control that major thrust and that minor thrust. Some engines or some pistons have coatings on them, and the coatings are designed for a couple of different things. One of the most important things on the coating, many of them have coatings on the skirt, and that is to aid in the lubrication process during a cold startup. So this moly coating on the skirt of the piston is actually designed to protect the engine, the piston, and the cylinder wall on cold startups. Why cold startups? Because on a cold startup, the oil has all run to the bottom of the engine. It's sitting in the oil pan. When we start that engine and the crankshaft starts flinging oil all over the cylinder walls, that moly coating no longer takes place takes effect, because the oil then provides a film in between the skirt and the cylinder wall. The ceramic coating on the top of this piston is designed, I believe, to control heat. So that ceramic coating on top of the piston will withstand more temperature. And you see the concave in that piston identifies that this is most likely a piston from a diesel engine. So diesel engines have much higher compression, much higher temperatures. So they would require ceramic coating like this to protect it from too much temperature. Changing the piston alone can affect the compression ratio. So we identify the compression ratio by looking at the size of the combustion chamber. So we take the size of that combustion chamber, usually in cubic centimeters, and then we identify the displacement of the piston as it sweeps from bottom dead center to top dead center. And we divide that volume by the amount of volume of the combustion chamber, and that gives us a compression ratio. So what that means is the size of the combustion chamber in this example is 1/10 of the swept volume of the cylinder. So that can be changed easily by adjusting the type of piston you're using, whether it's concave, flat, or domed, because any of those changes would affect the size of the combustion chamber. I'm going to stop there for now. On part 2, we're going to get into piston rings and discuss piston rings, how to install them, how to measure them, how to identify them, how to orient them, how to index them, and all that fun stuff. So I hope you guys contact me with any questions about this session, and please email me any other questions, comments, or concerns about this slide or PowerPoint, and I will be getting you guys the next part of this as soon as possible. I will see you on Tuesday. I would expect Team A to see me on Tuesday in the lab, and I plan on getting some more of these done before then. So have a good weekend, y'all, and I'll catch you later.